Okay, so on my behalf and on behalf of Isabel Oitavan, welcome to this session on automated proofs in mathematics. We thank the four speakers, Paulo Oliva, Michael Kenyon, Pedro Quaresma and Wilfried Sig, who kindly agreed to be here. And we thank the audience for joining us in this session. Without further ado, because it's important to stay on time, we move to the first presentation that you can already see. Paulo Oliva is a world-leading expert in mathematical logic and proof theory, working at Queen Mary University of London. He's also a great friend with close collaborations with Logic Group in Lisbon. And in the next 15 minutes, we take a big leap from Prover 9 proofs to human-readable proofs and experiments with residuated monoids. Please, Paulo, go ahead.
Thank you very much, Jada. Can you hear me well?
Yes, perfect.
So this is some work that Rob and I did about 2-3 years ago, experimenting with Prover 9, which is an automated theorem prover, and trying to understand the proofs that we got from Prover 9. So I think it was quite an interesting case study using some algebraic structures related to some logics. And that's what I'll try to talk about today. The main thing to understand here, and the main discussion that I want to prompt, is the difference between machine proofs and human proofs. And this really I hadn't come across this before I started playing with Prover 9, and realizing that Prover 9 can be really good at finding proofs that humans hadn't been able to find before. So we found some new results about these algebras. But the issue is that the proofs that we got essentially just told us that the theorem was true. We couldn't really understand the proof. So it's just hundreds of lines of paramodulation and steps that was difficult to understand. So we wanted to see how to take those proofs, machine-generated proofs, and turn them into understandable proofs, proofs that give us some insight into the theory. So in a machine proof like Prover 9, every line in the proof is treated in the same way. So every step in the proof is a lemma. Whereas for a human, we try to understand the main steps in the proof, and we call these lemmas that we hope to use later. So we think of lemmas as things that we can reuse that are interesting in themselves. Also, Prover 9 just proves exactly what it needs to prove. Whereas for a human, we quite often, when we try to prove something, we generalize. We try to look beyond what we want to achieve and maybe prove something more general. And quite often something more general has a simpler inductive step that makes the proof simpler. So this generalization or abstraction is something quite difficult for an automated tool. The tool will just prove what needs to be proven, and that's it. And also in a machine proof, you don't really get any new concepts in itself. So the concepts that you feed in, the tool will deal with those and then prove something about those, but we don't get any new insights. And that's what normally humans do. So when a human is studying a theory, they may start with some concepts and they might come up with new ideas, new concepts that they think are interesting, and they might study those concepts or constructions in itself. And we came across all this when in this case study, which I think was really, really insightful and interesting. And that's what I want to briefly discuss today. So we started with some theorem or some conjecture in a logic. So we said, is this true in this logic? So we had a formula, we had a logic, and what we knew is that this logic was complete for a class of algebras. So we said, well, we can turn this theorem or this conjecture into an equation, and then we can try to see if that equation holds in that class of algebras. And that's where we use Prover 9. So Prover 9 gave us a machine proof of this equation that we then wanted to extract a natural deduction proof that we could actually understand about that logic. And that's what we did in a few case studies, and I just want to talk about one of those here today because I only have 15 minutes, which was the double negation of double negation elimination. So the double negation of double negation elimination, it's provable intuitionistically, but it needs contraction. So you need to use this an assumption twice. In Łukasiewicz logic, or in intuitionistic Łukasiewicz logic, you don't have full contraction, but you have an axiom called divisibility. And our question was, can one prove this just using divisibility rather than using full contraction? So we turned that conjecture into an equation, and then we looked at for a proof in the class of bounded hoops, which are sound and complete for intuitionistic Łukasiewicz logic. So if you haven't heard of bounded hoops before, so these are simply residuated monoids. So a monoid structure with an implication or subtraction, if you can think about this, with an ordering. And together with this and an axiom which is called divisibility, which is on the right here, that says if an x is bigger than a y, then x can be decomposed as y plus the difference between y and x. Okay? And this algebra is called a hoop. And if you have a top element, this is called the bounded hoop. And this algebra characterizes intuitionistic Łukasiewicz logic. So because Prover 9 is really good at dealing with equational theories, and the theory of bounded hoops is an equational theory, we just fed in that equation into Prover 9, and Prover 9 was able to find a proof of this in just a few minutes. But then we had these hundreds lines of paramodulation that we couldn't really understand. We just knew that the result was true, but not much more than that. So this is just a snapshot of some few steps in the proof. So if you look at this, it just treats every single step in the proof in the same way. There's no new insights. There's no really special treatment for any of these lines. Every line in the proof is the same. And what we wanted to do was to try to understand that proof. So how did we go about doing this? We started noticing that a few patterns appeared again and again. So we looked at things like, for instance, A tensor A implies B appeared very, very much in the proof. And a few of those things, like for instance, A and A implies B, were already known concepts. And this is called weak conjunction. So A tensor B is the strong conjunction, and A tensor A implies B is a weak form of conjunction. And the dual of these, B implies A, can be also, it behaves also as a disjunction. It's called the strong disjunction. But we also found the strong implication and the NOR, so, or Peirce's AMPHEC. And these were the connectives that kept appearing again and again. And what we did was to try to study those in itself. So we picked every lemma that was about one of those connectives and try to think of these as things that deserve attention in itself. So we say, let's prove some lemmas about those new connectives. So we found these new concepts. We proved lemmas about these new connectives, especially things about symmetry, commutativity, and so on, things that looked interesting to a human. And we would prove those, add those new lemmas as axioms to the theory, and then try to prove the result again. And this became a kind of a cycle where we were just enriching the theory with the lemmas that we found out about this concept that we also discovered. And what we ended up with was a proof of this that we could finally understand based on a very simple and interesting lemmas about those connectives. So for instance, lemma 4.7 says that the AMPHEC, the NOR, is commutative. It's not something that is obvious, but it's an interesting result in itself. And using those lemmas, we could then finally obtain a few lines of a proof of the double negation elimination in intuitionistic Łukasiewicz logic. So we did this and a few other case studies about continuous logic, about the residuation of strong conjunction with the weak conjunction with strong implication, things that were not known before. The prover 9 found the proof, and we essentially tried to turn the prover 9 proof into a human readable proof. So in conclusion, I think what we did was to successfully mine or extract human readable proofs from machine proofs using this process of extracting new concepts, proving lemmas about those new concepts, enriching the theory with those extra lemmas, and then trying to prove again the same result, but now with these extra lemmas. And usually we got shorter and shorter proofs until eventually we had proofs that we could understand, and that gave us some insight into the theory. So this meant looking at derived concepts and trying to recover this proof plan that normally a human would do. So we even used as I said, the tool to do proof refactoring. So adding those lemmas and enriching the theory. So there are other people that I know are working in this kind of area. And one might also think of using AI or machine learning to try to spot what are the interesting theorems, because I'm using some vague words like interesting, new, or things that a human would find interesting. But how do we identify those? And I would say that really I think the main message here is how powerful I think Prover 9 is. And this is due to the late Bill McCune that developed a tool that is incredibly fast and able to find some new results in equational theories that really surprised us. I think that's it. I'll leave a few minutes if anyone has questions.
Thank you very much, Paul, for such a great talk. We have a few minutes for questions. Maybe if the audience has questions, can write them in the Q&A that we have in the bottom of the page. Meanwhile, I have a comment. There are many people here in Lisbon, researchers and PhD students, that are working hard on improving and developing new features to Prover 9 and this new version, the Prover X. And if I'm not mistaken, João Araújo and Michael Kenyon, and Michael Kenyon is next speaker, I think they were working on a package that tried to translate Prover 9 proofs to proofs that could be readable by a human. So I don't know exactly, but it seems that it could help this process here, Paul. You also told us that we have here just one case study, but it seems that we have other case studies. Do you think there is any hope in trying to find a kind of more general approach to cover other contexts?
Yeah, I have no doubt that this can be applied in many other areas, and I'm really curious to see what people in Lisbon have been doing in terms of extending Prover 9, because I think it's an amazing tool, and I have no doubt it will have an impact. And I think that, I mean, what you're doing was quite ad hoc and just following our intuitions, but I think a more kind of general theory of this process should definitely be developed to maybe even automated, so that one can automatically extract human readable proofs from these proofs.
Mm-hmm.
So I can see a question by Oliver.
Oh, yes,
Coleman.
yes.
Can you imagine automizing the concept building up? Yeah, so I think, Oliver, this is what I think some people are working on. I don't have the reference on top of my head, but I can try to dig that out. But I heard of people trying to use AI to automatically extract new concepts. So this process of abstraction and identifying kind of interesting patterns automatically is something that people are definitely working on. And I think it can be automated as well with all the tools that of machine learning and AI. Yeah. So Pedro has his hand up. I don't know if, do you have a question, Pedro?
Yes. You spoke at a certain point shorter and shorter proofs. Do you mean that you found the set of rules that were used and in the proof, and then reused the prover with that smaller subset, or what
Yeah,
do you
exactly.
meant by
So,
that?
yeah, exactly. So the proof that we got at the end was actually shorter in some sense than the original proof in two ways. In the first way is that the theorem prover quite often proves again and again trivial steps. And for us, the trivial steps, we just made them basic lemmas, and we used those basic lemmas freely, which meant we could save a lot of lines of proof. But also, some lemmas were used again and again in the proof as well. And by proving those and reusing the more abstract version of the lemma, we could again shorten the proof. Yeah.
Ah, okay. Thank you.
And Paul, in the end, you were talking about the meaning of new and interesting theorems. And it seems that also Pedro Quaresma, that is one of the speakers, is probably talking about that, some measurements to...
Looking forward to that.
So it's nice to open the curiosity of the next talk. Michael, do you want to say something, please?
Yes, I just have a quick question for Paulo. So you mentioned that in your examination of the first proof, that you noticed certain terms popping up that happened to be the commonly studied connectives. Was this because the proof was rewriting them in terms of defined functions, or was your proof entirely in terms of the original signature?
No, the proof, the original proof from Prover 9 was entirely based on the primitive connectives.
Oh.
And then as we noticed these connectives, these derived connects reappearing, then we defined them and we extended the theory with those connectives and then tried to reprove again with lemmas about those connectives and so on.
Okay, so what I was particularly wondering is in your later iterations then, when you introduced the connectives, were you having Prover 9 rewrite terms in terms of the new connectives as often as possible, or was it simply immediately expanding everything in terms of the original signature?
I think the Prover 9 was trying to use if we added the derived connectives and then we added the lemmas about those derived connectives, you would try to use those lemmas as well as the original.
Okay.
Lemma. So it was kind of trying both things, and it's difficult to know what exactly Prover 9 is doing.
Yeah, there's some ways of fine tuning that, in fact, so that you can
give priority to one or the other.
Yeah, so that you can give priority, for example, to your defined functions instead of the original ones, so that it will tend to rewrite in terms of those whenever possible. And that's what I was wondering if you were doing.
Yeah, no, we haven't done that. We're just using the default configuration of Prover 9.
Gotcha. Okay.
Yeah.
Okay, and we have some PhD students here in the audience. Just to say that Paulo Oliva also has these kind of experiments, not just with Prover 9, but also with MACE4. And some people are working on these tools. So I think you are going to...
Yeah, I didn't mention, but we did MACE4 as well as just trying to refute. Whenever we weren't sure if something was proved or not, we would also run MACE4 in parallel just to make sure there were no counterexamples.
Yes. Okay, I don't know if there is any, we have just 1 minute, a short question or comments. Okay, if not, to keep with schedule, we welcome the next speaker. Oh, yes. Thank you very much, Paulo. Thank you.
No worries, it's a pleasure. Looking forward to the next class.
Okay, so the next speaker is Michael Kenyon. Michael Kenyon is a leading expert in automated reasoning. He's in Colorado, University of Denver. Good morning, Michael, and thank you for being here. I think it's 8 o'clock in the morning.
Yes.
Michael has strong connections with the computational algebra community here in Lisbon, and we are quite fortunate to count on him to teach automated reasoning in our PhD at Universidade Aberta. Today, Michael brings us strategies for proof simplification in automated theorem proving. The stage is yours, Michael.
Okay, well, yes, good morning, everybody. I'm actually not in Denver today. In fact, while I'm here in Lisbon, I'm actually visiting New Mexico, where I'm visiting Bob Viroff, who is my oftentimes collaborator and whose name is going to come up a little bit later in this talk. So I'm going to talk about proof simplification and specifically using Prover 9. And so my talk happens to dovetail very, very nicely with the previous one. I thank Paolo for setting things up so well for me. That was very nice of you, Paolo. So let me talk a little bit about what I mean by proof simplification and get a little bit into this. So first, just a general remark, because we're going to hear a little bit about both automated theorem proving, and we've already had one talk about it, and a little bit later, interactive theorem proving. And more they're becoming an integral part of mathematics. Some really major results in the theory of perfectoid spaces, for example, have just been verified with interactive theorem proving. I'm going to focus on automated theorem provers because that's what I know, and I'm really not an expert at all in the ITP setting, although some of the broad principles apply. Now, I gave a talk somewhat related to this about 4 years ago at the Hilbert workshop at Nova. And so for those of you who were there, and I see some in the participant list, a few people, I apologize for the overlap. But on the other hand, I don't expect you to remember everything I said 4 years ago. So I think it's probably okay if I repeat myself a little bit. Okay, and my discussion is going to center around Prover 9, just as Paolo's did. Now, in principle, one could do this for any automated theorem proving system. Now, if you talk to computer scientists, they generally don't like Prover 9. It's because to them it's outmoded. It's legacy software since it's no longer being developed. Bill McCune passed away several years ago, and the ATP system of choice nowadays for many people is either E or Vampire. However, none of these other systems, as far as I know, really support proof simplification in the way that I'm going to be describing it. Also, Prover 9 is more popular with mathematicians because we can actually read the input, unlike the other systems where it's very difficult to read the input if you're a mathematician. Now, in order to make sense of the methodology that I'm going to be describing for proof simplification, what I have to do is back up a little bit and talk about the main loop that is used in automated theorem provers. Almost all of them use some variant of the one I'm going to describe. I'm not going to go into details about it, just describe it in very general terms. And so we're going to assume now that we're ready to start searching for a proof. And what exactly happens in an ATP system, a general ATP system that makes this work? So there are three objects that are the key to the process of making inferences. There's the given clause, that's really the important one, the set of support, and the usable list. Now, the given clause is the one that actually controls what inferences can be made. And this is important for proof simplification, as we'll see here in just a couple of minutes. I'll explain first what the other two are so that the given clause actually makes some sense. The set of support, you can just think of it as being a list of clause that is sitting there waiting to be selected as the given clause. They are clauses which have been derived, kept, and now they're waiting their turn to make inferences with. But they just sit there and wait their turn. The usable list is the list of clauses that are available for making primary inferences with the given clause. And so what happens in the main loop, I won't write it as a formal while loop, I'll just describe it. In each iteration, a given clause is selected from the set of support, it's moved to the usable list, and then inferences are made using the given clause and all the other clauses in the usable list. So for example, if your primary inference is paramodulation, you use the given clause and one of the other usable list clauses to do a paramodulation and derive brand new clauses. And then those clauses are either kept or not, depending on if they repeat previous things and pass various retention tests. Now, Bill used to say, and I heard him say it quite frequently, it's all about the given clause. He was actually the person who came up with the given clause algorithm that almost all ATP systems use nowadays. But the real issue is, how does an ATP system choose the given clause? There are a lot of clauses sitting there in the set of support. How does it decide which one to pick? Well, there are many strategies. Common ones that in the early days of automated theorem proving were breadth first. A breadth first search just simply takes the oldest available clause. A lightest first search is another one, where you take the one that has the least number of symbols. Okay. Most ATPs, however, have a default scheme, which is a mix of these things, and take an old clause, take some light clauses, things like that. And users can change this in almost any system. Okay, so here, just to give you an example, is a typical proof header from a Prover9 proof. I actually, if you're going to ask me what this was proving, I don't remember. I've forgotten. Based on the length of the proof, this was probably a proof in quasi-group theory. This, by the standards of, by the way, I should mention that by the standards of quasi-group theory, this is a typical proof length, 800 clauses. In fact, it's almost considered short by quasi-group standards. A couple of the three stats there that I want to point out are the length of a proof, the level of a proof, and the maximum clause weight. The length of a proof is the number of primary inferences that were made. Now, this does not include rewriting, for example, or other secondary inferences that are made after a primary inference. The level of a proof is the longest chain of inferences from the empty clause to one of the input clauses. So you can imagine a proof as being a graph where each clause has parents that are pointing at it if they were used to derive that immediately to derive that clause. Now, if you visualize the graph, at the bottom is the empty clause, meaning you found a contradiction. And at the top are the inferences. The longest chain is called the level. And the maximum clause weight is just exactly what it sounds like. It's the number of symbols in the longest clause. So this, for example, typical proof header had a really large maximum clause weight. 89 is quite large. All right, now what I want to talk about for proof simplification here is proof sketches, okay? This is a technique that is designed by Bob Viroff, and it's really the key to simplification. The idea is that maybe you have a theorem you want to prove, but it's easier to prove in a more specialized setting, okay? Then it can be the case that the proofs of your general and special settings might have a lot of features in common. So wouldn't it be great if you could do the special case that's easy first and then guide the search for the general case using the special cases proof? That's what the idea of proof sketches is based on. So for instance, you want to prove a theorem about distributive lattices. It's easy in Boolean algebras, so you prove it there first, and then you work your way up the lattice hierarchy until eventually you come to, you actually are able to prove the theorem that you're interested in distributive lattices themselves. And each time you use the previous proof to guide the new search. And how is that actually done? Let me skip this one. How is that actually done? That's actually done by what are called hints, okay? Proof sketches strategy is implemented in two ATP systems, Prover9 and E. And the idea is the same. The theorem prover checks to see if any new clause subsumes an existing hint, okay? And if so, it's marked as a hint matcher. Now, so what? What does that do for you? Well, here's the idea. These are supposed to be milestones toward a proof because they were things that occurred in a previous proof. So they're probably important. So the idea is if there is a hint matcher in the set of support, select it right away. Okay, and if there's more than one, then come up with some scheme for selecting them. But select hint matchers before you select anything else, because you want to follow the earlier proofs as much as you can. Okay, all right. Now you might think that if you extract hints and then you run Prover9 again with exactly the same input, but now you have some hints to follow the previous proof, you might think that Prover9 would find the exact same proof as before, but that's not what happens. Because you've changed the given selection scheme, you're now selecting hint matchers off of this set of support sooner than you did before. This has a butterfly effect, and it actually changes the search. So the proof that you get is, generally speaking, going to be different. Okay. Now, an automated theorem proving proof, an automated theorem prover's proof is called stable if, when the hints are used as a sketch, Prover9 finds essentially the exact same proof. Okay. But the first proof an ATP finds is usually very complex and very unstable. Paolo basically mentioned this in his talk. This is what happens when the very first proof that pops up. So the idea behind simplification is to rerun the same Prover9 job, but use hints. Now this almost always, there are exceptions, but this almost always results in a much simpler proof, where you have to decide what you mean by a measure of simplicity. You can repeat the process then several times. And sometimes the length and the level and various other features will increase, which means the proof you're getting is more complex. But that's okay, because if you keep going, sometimes they'll just go down later, meaning the proofs, the next proof you get may not be as simple as the one you just had, but if you keep going, sometimes you'll get a simpler one. And you can continue this process indefinitely. Now, what we do in practice, and this can in fact be automated with things like Python scripts and so on, is what we do is we restrict the search so that Prover9 does not wander too far away from the preceding proof. We want it to find a simpler proof, but we don't want it to go off in a completely different direction where it ends up finding a proof that's ridiculously complicated. Because presumably the existing proof is not too bad, it's just got some complications to it that are unnecessary. So the way to do that is to control the maximum weight. We squeeze the maximum clause weight and tell Prover9, if one of the hint matchers is too big, don't select it. Okay, try to bypass it. Find a different proof with shorter clauses. Invariably, okay, 99% of the time, Prover9 will find a much simpler proof. And then we can iterate this process until we're satisfied. So simplest proofs I find typically have about 25% the length of the original proof. So in the very first header, for instance, there was a proof that was length about 800 something, right? After I simplified it using what I'm describing, it got down to about 200 steps. And that was as far as I could take it before there wasn't anything else I could do. So let me just wrap up by talking about measures of simplicity. So what are some different ways that we can measure the simplicity of a proof that's built by an automated theorem prover? Because I'm being very vague what it means. Well, you could count lots of things: the total number of inferences, the branches of the proof tree, clause weights, and so on. Many other, presumably a reasonable measure of simplicity is some combination of these things. And there's no reason to assume that simplicity in one context is the same as simplicity in another context. So it could depend very much on the problem at hand. If you look at the literature on proof simplification, and I'm guilty of this as well, many have advocated using length as the only interesting measure of simplicity. But that's a problem, because proof length does not count rewrites. And let me show you, just to kind of finish up here, let me show you a toy example of how deceptive this can actually be. Okay, so here is a ridiculous input file. It is ridiculous because this is proving something that's completely stupid. There are two axioms here, f of a equals a, g of a equals a, and we have hyperresolution as the only inference. And what we want to do is prove P of a and Q of a, where P and Q are two predicates. All right, well, that's trivial for a human. There's nothing to do here, okay, for us. Let's look at what happens in the two proofs. Both proofs have length 7, okay, but notice the difference. The proof of Q of a has a step here, a hyper-resolution step that has a whole bunch of rewrites. In fact, it has, I think, 10 rewrites in it, okay? The proof of P of a does not. It has only 2 rewrites, okay? Sure, they have the same length, but presumably one would consider the second proof to be simpler because there are fewer rewrites that are going on in this thing. So whatever measure of simplicity we use, we should keep track of secondary inferences as part of the moral of this. And I've been guilty of not doing that sometimes. Okay, finally, let me talk about humanization, just to finish up, dovetailing with the previous talk. One of the practical goals of simplification is exactly humanization, okay? Because we do want to sometimes make our proofs that are palatable for journal editors so that they will actually accept our papers, okay? But there are exceptions to that. Here is an actual proof header from an actual proof. This is the current record. Notice the length of the proof, 72,837 steps, okay? Don't pay any attention to the clause weight, that's not realistic. There is no way that anybody is going to humanize this, okay? And I have no intention of ever doing so. But at least if we're going to archive it, we should try to keep things as simple as possible. All right, I'm done. Thank you very much. I'm sorry I went a couple of minutes over.
Thank you very much, Michael. If there are questions or comments, you can write them in the Q&A. Oh, Michael, just a comment. Well, we have just 3 minutes, so
I'm sorry.
There is already a question here. From Paiva. Can you read it, Michael?
Oh, yes, I've got it. Yes, if we add some extra axioms that result from the initial assumptions, we may reduce the number of steps of the prover 9's proof, right? Yes, and that's exactly the point that was made, I think, in the previous talk. Then we can, when we humanize, then we do indeed have some lemmas that go with the extra axioms. Now, there are exceptions to that. There are times when adding extra axioms steers the search in a weird direction, and it actually gets longer. I've seen this happen more times than I care to admit, and there's no special reason for this other than just the butterfly effect from changing the search space. But yes, generally speaking, it is the case that rerunning with additional axioms can also help if your goal is humanization.
Sorry, I don't think I can type a question in the Q&A. I'm not sure why. Is it okay if I just...
Well, you can...
You're a panelist, so you can just ask.
Yeah, I don't think there is an option for me to write. If I can just add a comment that we were a witness of the power of these sketches, because when we were looking at this weak conjunction and strong implication, we couldn't find a counterexample to the fact that weak conjunction residuates strong implication, but we couldn't find a proof either. So we waited hours with prover 9 and never got a proof. And then we sent it to Bob Verhoff, and in a few days he came back with a proof, and he said that he used his proof sketches. So I'm not an expert on them, but I can assure that they must be really powerful.
They really are, yes.
And Michael, just a curiosity about this work on humanizing the proofs. Did you have success with the, I think it was Explain that you were developing, or what is exactly the art?
Yeah.
Or where you can reach?
Yeah, actually, I'm probably the wrong person to ask about explain, because I was sort of not really part of the developing group. I was more sort of watching it from over the top. Yeah, Joao is probably a better person to ask what the current status of explain is. I actually had some trouble running it myself, not because of anything other than just technical reasons. So.
Okay. Well, we are running out of time. Thank you very much, Michael. Isabel, please, can you go ahead?
I take it over to introduce the next speaker. It's Pedro Quaresma. I don't know, Pedro, if you can share your slides. He is from University of Coimbra, and is going to tell us about new and interesting theorems. Please, Pedro, when you are ready.
Sorry, I lost myself.
Yeah, no problem. You can wait a moment.
Okay. Share. Okay, you should be seeing.
We are seeing it, yeah.
Okay. So this is a quite different talk in certain sense, but it is related to the first one when the speaker said something about the IETPs only prove theorems. They don't find new theorems. And this is one open problem. The problem 31 of Larry was the automated reasoning 33 basic research problem. He asked for what are the properties that can be identified to permit an automated reasoning program to find new and interesting theorems, as opposed as the normal use of ATP that is proving conjectures. So two big problems in one sentence. How can we discover new theorems? Is it possible to deal with that? And if we can discover new theorems, how can we select the interesting ones from those that we discover automatically? And the automation or automated generation of interesting theorems is something that is doable and is being done for quite some time now. I'm referring to a set of bibliographic references. So the first one is Puzzes and Others, 2006, Automated Generation of Interesting Theorems. In these, Puzzes identify four ways of generating new problems. Inductive, from facts to conjectures. So it is positive in the way that is stimulated by observations in the domain, but the problem is that can be unsound. Generative, mechanical manipulation of symbols. Okay, it can generate higher fraction of theorems, but again is unsound. Manipulative, we will speak about that in a few seconds, in a few minutes maybe. Generate conjectures from existing theorems. So we have a set of theorems. Let's try to manipulate them in such a way that we can find new theorems. If the manipulations are satisfiability preserving, then we are producing theorems. But here we begin to have the problem, okay, but we can generate many boring theorems without any interest. And the last one, the deductive approach, application of sound inference rules to axioms. It is sound. We can, given a set of properties, try to generate all the theorems that they are that are derivable by this set of tools by forward chaining. But as we will see, the problem is that we will generate many uninteresting consequences. So the two things go together side by side, the generation of new results and the measure of interest in the theorems that are generated. A group of researchers around Gao began to work on this sometime, and they continue to work. They have the first paper even before 2014, around the late 90s, with Geoff Sutcliffe from Miami. And then they have papers, and now more recent papers, and they use now strong relevant logic forward deduction approach. And the idea about behind the algorithm is they choose a domain, so they prepare that the domain, the preparation phase, a design model of formal theory, begin to make deductions. From the deduction with strong relevant logic forward chaining, they try to abstract theorems in the sense of already filtering the uninteresting variations of the same theorem to abstract theorems, then excavate abstract theorems. Okay, this is the term they use to filter the theorems, of trying to find the interesting candidates and feeding again the deduction mechanism to find new theorems, to abstract theorems, to excavate the interesting ones, and so on and so on. This is something that, as said in the previous talk, this is in many ways domain specific. For instance, if we pick the geometry automated theorem provers, and more specifically deductive databases, the geometry deductive database method as developed by Xu and others in 2000, and also integrated in the software, the GGEX software in 2011, we can find the process of find the fixed point, saying that from the set of rules of the deductive database method, and a conjecture, given construction, geometric construction, we began to applying the rules to find facts about that construction, and apply again the rules. And this algorithm, this loop, will reach a fixed point. And this example give us for this construction all these facts, parallel lines, perpendicular lines, congruent segments, and with this software it is interesting because we can click. Sorry, I didn't want to click, and I click. Okay, no. Okay. We can click, but in the live software, not in the presentation. And we relate the new property with the construction. And this is, for instance, one actual software where we can have this process of discovering new theorems. In here, they don't try to filter the information. These deductive database are using always forward chaining process, but to prune the tree, to avoid the explosion of cases, sometimes they use also backward chaining and the model. There are some techniques to avoid also the explosion of situation of cases. Continuing, There are also some approaches in terms of geometry, but using algebraic approaches. For instance, Thomas Récio and Velez, automatic discovery of theorems in the elementary geometry. This is about finding missing hypotheses so that a given conclusion follows for a given incomplete set of hypotheses. Here, the problem is that they do it by algebraic means that is translating the geometry construction to an algebraic set of equation. So the proof is a black box with a yes or no, or this in this case, the missing hypothesis. Also, some work done by Botana, it is related also with Thomas Récio, in terms of locus equations, finding the equation behind the locus, and more recently, Zoltan Kovacs and one student, a PhD student of him, are trying to integrate that in a well-known dynamic geometry software, the GeoGebra. So they try to, again, by algebraic means, so they have to define equal in general definition of a point to avoid the floating point difference. And then they can ask for a given construction properties, new properties regarding lines, circles, parallel lines, congruent segments, and that kind of properties in geometry. Going to interesting theorems, the things are related. Again, Puzies et al., the same paper, they in here, Puzies identify that to classify a theorem as interesting, we have to look for a set of characteristics of the proof. For once, they, in a proper assessing, they try to discard the obvious tautologies. Then they have weights, or they have characteristics of obviousness, weight, complexity, surprisingness, intensity, adaptivity, focus, usefulness. The weight was already referred by in the previous, and the other are a set of measures, sometimes not very easy to measure, but that can be used to try to find the interesting theorems on the set of all the generated theorems. And for instance, Colton in 2000 made a survey of some programs that were trying to do this kind of process. They were all manipulative in the sense they generate conjectures from existing theorems, and they have some, and in some specific domains, and they are capable of filtering, again, with this, more or less the same kind of ideas. Pre-processing, discarding obvious tautologies, surprisingness, measuring new relations, complexity, the number of distinct function and predicate symbols, and usefulness. And if we go to the work of Gao, the same kind of ideas are behind the work of Gao. They have already in the last papers, 2018 and 19, they already have formulas for all of these, and they explore several corpus, and with those several corpus, they already arrange some kind of formula to find the interestingness of theorems. They are using the degree of logical connectives in the empirical theorems, the propositional schema of a formula, the abstract level of predicates and functions, and the deduction distance. These concepts are all defined by Gao, and with these they managed to already to have some automatic, let's say again, this is an idea to have a program doing that automatically. So the idea is that they we can have a formula that the program applies to find to separate the boring for the interesting theorems. We are going to work in a different corpus, and the idea that we begin to explore is that a theorem age in the 1,000 of geometric theorem provers, a database of problems in geometry, is interesting if it is provable from other theorems. And it is necessary to prove other theorems. This is the deduction distance of Gao. This is related to at least to deduction the distance of Gao. So this is something that we are now working. This is something that is open problem, still many things going around, but now nothing really concrete. And let's say that I have a proposal for grading proof, but this is not okay. I don't have the time to do this. So okay, not this. Okay, interesting theorems remain an elusive question, but we are working on it. Is the conclusion that I want to have from my talk. Obrigado.
Thank you, Pedro. Actually, we have here a very rigid structure, so we have still time for a question, some comment. So feel free here from the room, you can just ask. From the assistants, just write to us and I think we have one question, Pedro.
I guess you tried machine learning. For the moment, no. For the moment, we are dealing with the formulas, with the mining, in certain sense, of the proofs in terms of the predicates, the functions, the connectives, the schema of the sentence that we are using. But I will say that at a certain point we will go in that direction. But for the moment, no. For the moment, this is not some sort of machine learning trying to classify the problems in some way.
Thank you. I think we have, okay, it's just okay. Thank you, Pedro, again. Very nice talk with a lot of information. It was nice to listen. And we move to the next and final speaker. Wilfried Zick. Maybe you can already share your slides if you like. So Wilfried Zick is a colleague from Carnegie Mellon University. And he will speak about human-centered theorem proving, interactive and automated. Thank you. Zick, please.
Well, thank you, Isabel and Gilda, for organizing this workshop. And I also want to thank all the people who have been involved in my project over quite a number of years. And I found it sort of interesting that Paulo's talk and Michael's talk were addressing issues that led me in the mid-80s to something completely different. So let me tell you, I was on Frank Fanning's dissertation committee, and his task in his dissertation was to translate proofs that had been obtained by Peter Andrews' mating procedure in higher order logic into natural induction proofs. And in the end, I thought, this is hopeless. How can you ever use this? And doesn't one have to have the strategies for constructing natural deduction proofs in the first place? And so that's why I started to do something different, namely to think about how can one automatically generate natural deduction proofs. So that was the starting point for me. So 1986 or 1987 or something like it. In any event, if the title of my talk indicated to you that I'm considering computer-based theorem proving, you're right. If interactive suggested to you that some interplay between human users and the computer system is envisioned, then you're right again. The automated part of the title is not easy. The computer system is also to search for and find proofs on its own. The central issue concerning automated search is reflected in one direct question. What kinds of methods can be used? And two different methods or kinds of methods have been used, machine-oriented and human-oriented ones. The former, machine-oriented techniques, have been mostly refinements of resolution, and the work that was reported with Proof-9 supports exactly that point. The latter, human-oriented techniques, range from pure heuristics in the sense of Newell and Simon to incorporating aspects of natural deduction, as was done by Bledsoe and his students, Boyer and Moore. I have been pursuing the human-oriented direction with a sharp focus on natural deduction techniques. That finally explains the human-centered part of the title. The methodological issues I pointed to are, or I will argue, should be at the heart of proof theory. That subject has two faces. One is directed towards the mathematical investigation of formal logical calculi, and mostly done in the pursuit of Hilbert's finitist consistency problem. The other is directed towards the formalizability of mathematical proofs in calculi that reflect crucial aspects of their structure and construction. Both, it seems to me, are important, but the second has not been followed through in a systematic and purposeful way. And yet, I would like to emphasize, this second direction has its roots in considerations that precede the very beginning of the subject of proof theory. Indeed, Hilbert called in his Zurich talk of September 1917 programmatically for a theory of the specifically mathematical proof, and took important steps in his lectures of the following winter term in 1917-1918. And here, just to amuse you, perhaps, is a picture of the assembled Swiss and German mathematicians at this meeting in Zurich in September of 1917. And you see in the middle, Hilbert. And in the back somewhere is Paul Bernays, and to the right of Hilbert, well, 3 down the right, is Hermann Weyl. In any event, Gentzen, building on Hilbert and Bernays' later work that started in 1922 really, considered as late as 1936 formal derivations in natural deduction calculi as images, Abbilder, of mathematical proofs, and viewed the proofs of mathematical practice as the objects of proof theory. And he wrote this in 1936 in the paper in which he established the consistency of elementary number theory. So for me, the crucial question is then this: how can one represent the remarkably rich domain of mathematical proofs in a systematic and also mathematically rigorous way? What could be a theory of the specifically mathematical proof? As I mentioned already, the first steps were taken in Hilbert's 1917-1918 lectures. In those lectures, he, on the one hand, pursued number theory and analysis in a formal way in the framework of Principia Mathematica. And he had deep logicist aspiration. He wanted to show that mathematics really is a part of logic, logic conceived as Russell Whitehead, Principia Mathematica. On the other hand, he presented the syntactic formal framework in mathematical, precise and rigorous way, raised important questions of semantic completeness and decidability. These lectures, not the later book of Hilbert and Ackermann, is the real starting point of the modern subject of mathematical logic or metamathematics. In the following 2 years, that is after 1918, Hilbert and Bernays rejected Russellian logicism. They articulated Hilbert's finitist consistency program at the very beginning. Sorry, that was not intended. Of 1922, and carried out the first sophisticated proof-theoretic investigations that established the consistency of a part of elementary number theory, which we now call primitive recursive arithmetic. However, most important for us is the fact that Hilbert and Bernays replaced the logical calculus of Principia Mathematica as the framework of representing mathematical proofs. They formulated a differently structured axiomatic calculus, and I will describe it and its evolution in Genson's rule-based natural reduction calculus in the first part of my talk, theoretical framework, natural deduction. At the end of that part, we will notice that the natural deduction calculus reflects important structural features for constructing proofs, but misses out on others, and in particular misses out on strategies for constructing proofs. That observation leads to part B, strategic framework, natural intercalation. This purely logical framework is then expanded in part C. It's titled Natural Formalization, in which I want to discuss briefly the formalization in a very natural way of the Cantor-Darmstadt theorem. In part D, I had intended to use that framework and suitable strategies for the automated proof of Gödel's incompleteness theorems. That part was titled Automated Search Gödel's Theorems, but it will be reduced to some brief remarks. So here is the overview. Part A, theoretical framework, natural deduction. Part B, a strategic, motivated framework, which I call natural intercalation. Then use that framework and expand it to a formalism that allows you to formalize in a direct and natural way the Cantor-Darmstadt theorem, and then part D, unfortunately, will be reduced to a brief remark. But before beginning the substantive discussion, I should mention that apart from the starting point I mentioned, namely the thesis of Frank Fanning and my reflections on it, the other starting point was pedagogical. I had the strong belief that constructing natural deduction proofs is an important and transferable skill. But I also had the experience that this skill is difficult to teach. So my naive idea was to use a theorem proof based on natural deduction as the background for an automated, intelligent proof tutor. So a student works in an interface, tries to construct a proof, finds obstacles, consults, enters a dialogue with the proof tutor gives the partial student proof to the theorem prover completes the argument, and then based on this completed argument, well, the proof tutor can give hints to the student. So that was a naive idea, and it didn't work out. And in the sense that I just thought, computer scientists, mathematicians must have natural deduction theorem provers around, so I just take it off the shelf and build the proof tutor. But that was not the case. In any event, so let me start with part A. And with a remark of Paul Bernays from that early period. At this point, the investigation of mathematical proofs by means of the logical calculus is brought to bear in a decisive way. This investigation has shown that the concept formations and the inference patterns used in the theories of analysis and set theory are reducible to a limited number of processes and rules. In that way, we succeed in totally formalizing these theories within the frame of a precisely delimited symbolism. And as I mentioned, in the lectures from 1979, 1918, Hilbert and Bernays used the formalism of Principia Mathematica. And let me just show you the axiomatic framework for just sentential logic. I mean, I don't want to go into ramified type theory and reducibility, whatever. I just want to look at the basic logical structures. And I do this just for sentential logic. So I'm sorry, this is a little bit blurred, but those are the axioms that were actually used by Hilbert and Bernays, you know this in German, for sentential logic. The basic connectors are disjunction and negation. the conditional is defined, and this defined version of the conditional is used in the formulation of the axioms. But in their experience with actually giving formal proofs in this framework, they found it cumbersome. And so they introduced a different kind of axiomatic calculus, and this is it. So just for conjunction and disjunction. So here you have a conditional phi error, psi error, phi and psi. And so it goes for disjunction. And if you look at it a little bit carefully, you notice what I wrote down on the left: and introduction and elimination, or introduction or elimination, are exactly what you're used to from natural reduction calculi, except that those are articulated as rules, not as axioms. In any event, what are the reasons for their articulation of these axioms? There is one pragmatic one. They thought they make the formalization easy, or at least easier. That was the first reason. The second reason was a methodological one. Namely, they wanted to articulate groups of axioms for the central logical connectors in the same way what Hilbert had done for the basic geometric concepts in his Foundations of Geometry. So articulate axioms for the basic logical connectors that are useful in proofs in the same way in which Hilbert had articulated groups of axioms for these central basic geometric concepts in Foundations of Geometry. So there's only one remark I wanted to make about this, namely that the proof-theoretic investigations and operations they wanted to carry out forced them to a tree-like representation of proofs, which I think is interesting for the next step I'm going to show you. And you also notice that if one uses this calculus, it is bureaucratically silly. I mean, for example, if you have established a statement phi and a statement psi, then you would have to use modus ponens twice to get finally to the conjunction phi and psi. And it's exactly that bureaucratic silliness that is avoided completely in Gensen's natural deduction calculus. And here are the standard introduction and elimination rules, again, just for conjunction and disjunction. So, what did Gensen view as distinctive for the natural reduction calculus? It is not the interplay of introduction and elimination rules, but rather the making and discharging of assumptions. That reflected for him a crucial structural aspect of ordinary mathematical argumentation. And it is that feature that is incorporated in the now standard Gensen-Pravitz formulation by discharge functions that operate on the leaves of proof trees. I referred already earlier to the 1936 paper in which Gensen proved the consistency of arithmetic. But he also gave there a sequent, as he called it, a sequent formulation of natural reduction. Here we go. the rules, if you look at them, are exactly the same for OR introduction and OR elimination. What is the gamma on the left-hand side of the horseshoe supposed to do? Instead of having the dependency on assumptions of a particular proved formula indicated by the open assumptions in the proof tree, those assumptions are literally carried along in the proof. So those are the assumptions that have been used in the proof of phi. And notice, all the logical operations are happening on the right-hand side. So in particular, it gives you the possibility of making detours by introducing and then immediately eliminating a connective. And it is that making of detours that make natural deduction non-normal. But there is one aspect that is missed out in this particular natural deduction calculus, whether in the Gensten-Pravitz form with indicating assumptions, dependencies on open assumptions, so non-discharge leaves of proof trees, or in this sequent formulation. Namely, they miss out on the important feature of ordinary mathematical reasoning, namely that in ordinary mathematical reasoning, you make backward steps. And that leads me to part B. So, if you think about it, backward steps are involved when you're trying to prove negations, conditionals, universal generalizations. If you are teaching natural deduction, then those backward steps are, of course, heuristically suggested, but they cannot be properly incorporated into the syntactic natural deduction configurations. So the question is, first of all, how can we describe the problem that has to be addressed? That in an informal way, we want to close the gap between assumptions gamma and a goal phi by exploiting assumptions via elimination rules and simplifying goals via inverted introduction rules. That's what I have been calling intercalating. The logical problem is thus addressed by a species of forward and backward chaining. And here are the rules of what I call natural intercalation calculus. And I'll just do it for a number of elimination rules. And what does it do? You have assumptions, gamma, and what is written here to the right of the semicolon and to the left of the horseshoe is a sequence of formulae that has been obtained by elimination rules. And the sequence of these elimination rules is given to you if, as a matter of fact, the goal kappa is a positive subformula of an element in gamma. So elimination rules allow you to extract kappa from an element in gamma. So it's a sequence of steps that leads from an element in gamma to the goal kappa. But clearly, this works only and makes sense only if kappa is a positive subformula of an element in gamma. So let me give you a very simple proof of B and C from assumptions A and C, A arrow B. So those are the assumptions or premises. This is the goal. The first question strategically is, can one obtain the goal B and C by an elimination rule, or is it already contained? Well, it isn't. It is neither a positive subformula nor is it contained as an assumption. So you apply an inverted introduction rule, break it apart, that is, simplify the goal. And now you have on the left-hand side in this part to prove B from the given assumptions and to prove C from the given assumptions. And in this part, right-hand side part of the construction, you obtain C immediately because it is a positive subformula of A and C by the appropriate elimination rule. And similarly, you obtain matters on the left-hand side using the appropriate elimination rule for the condition. The translation into a normal natural reduction proof is given here. And the next step I'm going to skip. It indicates how in the real interface where we are using partial Fitch diagrams to represent proofs, the construction would actually carry it out. So the rules of this calculus do, in a certain sense, not generate proofs inductively, but rather partial proofs that may have gaps, and those gaps have to be filled. And the construction of proofs can be strategically guided by focusing on goals and seeing whether this goal can be obtained by elimination rules or whether introduction rules have to be inverted to simplify the goal. These intercalation calculi have interesting and important mathematical properties for both classical and intuitionistic first-order logic. They are complete. And the proofs that are obtained using these strategic guidance are actually directly translatable into normal natural reduction proofs. And it is that search procedure that has been implemented quite efficiently in a theorem prover proof search mechanism I call APROS, Automated Proof Search. So we have calculi for partial proofs that support a bidirectional and strategic proof construction in both intuitionist and classical first-order logic. What about constructing proofs in mathematics, the ultimate goal of our enterprise? And that leads me to part C. And it seems to me that I have to speed up my presentation. I'm running out of time in spite of the fact that I have plenty of it. And let me first tell you about Gensen's perspective on formalization. He thought it is given by an easy and direct translation. He wrote in this 1936 paper, the words of ordinary language are replaced by particular signs. The logical inference steps are replaced by rules that form new, formally presented statements from already proved ones. Only in this way, Gensen claims, is it possible to obtain a rigorous treatment of proofs. However, he distinguished between foundational and practical formalization. The former reduces the inferential steps to purely logical ones, whereas the latter allow much greater variety. Gensen did not suggest any particular additional steps that could be taken in mathematical arguments. However, his friend and fellow student in Göttingen, Saunders MacLean, investigated in his 1934 dissertation exactly this question in a systematic way. And if I had time, I would read to you how he envisioned this enterprise. He articulated this beautifully in a letter to his mother he wrote in 1934. In any event, let me move to the attempt of proving or giving you a sense of how we are proving interactively the Cantor-Bernstein theorem. Dedekind proved it in 1887 in the frame of his systems and mappings. We use Zermelo-Fraenkel set theory that emerged from Dedekind's framework. I formulate 3 steps to turn the foundational system ZF into a tool for natural formalization. There's first of all that every definition is associated with rules, introduction and elimination rules. Here you see the introduction and elimination rules for the power set operation. In the background, we have a hierarchical conceptual organization. That is, we take for granted for this interactive way of doing things what Paulo described as extracting from a machine-given proof. And then the final part is we use lemmas as rules. So lemmas of the form a conjunction of statements in the antecedent and a consequence. So pure conditionals, the antecedent, conjunction. And so as soon as you have verified the antecedents, the antecedent of the lemma, you can apply it as a rule to infer the consequent. And if one does so, one can, in a rather intelligible way, obtain a natural articulation of the proofs of the Cantor-Bernstein theorem and of Dedekind's fundamental lemma. So the Cantor-Bernstein theorem simply says that F be an injection from A to B and G an injection from A to A. Then there is a bijection, H from A to B. The sandwich lemma, or Dedekind's fundamental lemma, is this one. You have a bijection from a set A to a set E, and you have an additional set D that sits between E and A. So you have a bijection from A to E, and then the claim is there is a bijection H star from A to D, to this intermediate part. And this lemma is actually equivalent to the Cantor-Bernstein theorem. And okay. So I wanted to show you a diagram that indicates the situation of the Cantor-Bernstein theorem. You have a set A, a set B, you have a function that is injective from A to B, and you have an injective function from B to A. Now, just very elementary facts concerning functions and injective functions in particular allow you to argue that the image of A under F is a subset of B. Similarly, if you apply then G to F of A, you get a subset of A. And if you apply G to the whole set B, you get a set that is sitting in between A and the composition of F and G applied to A. Now, this just describes exactly the premises or antecedent of the fundamental lemma of Dedekind's. So you apply it to obtain from the given bijection from A to G, circle F of A, a bijection to G of B. G of B is, of course, of the same size as B, so you have a bijection between A and B. So, and it is that simplicity that is expressed in the final proof that we interactively gave. Here are the premises of the Cantor-Bernstein theorem, the verification of the antecedents of the fundamental lemma, application of the fundamental lemma, and some additional features of very simple lemmas. So what Paolo mentioned at the very beginning about the role of lemmas, that's what we are exploiting, and obtain an intelligible proof that is based on one fundamental fact, namely the sandwich lemma, and otherwise very direct facts, set theoretic facts, that anyone who has taken even elementary course in set theory would recognize as correct. But then, of course, in the interactive verification of the Cantor-Bernstein theorem, all of this has to be established. And to obtain this proof in this simplicity, we are building up matters through more than about 100 lemmas. That, of course, don't appear all in this final proof. Okay. Here another picture, and I wanted to illuminate what I described in generality for the proof of the Cantor-Bernstein theorem, namely that this is a classical way of doing proofs in mathematics. You know, the Pythagorean theorem is proved at the end of book 1 of Euclid's Elements. And this is the basic diagram that accompanies the proof. Not as colorful as in this edition by Oliver Byrne from 1850 or something. So what you want to see is that the triangle DCE and the triangle BAC are equal. And that is obtainable directly by the side angle side lemma that was established very early on in book 1. And then you only have to see 2 additional features, namely that this triangle, ABC, is half of the red square, that this triangle DCE is half of the yellow rectangle. And then you have the Pythagorean theorem with a few very simple inferences. The point is, some simple inferences that are of independent interest, and one central lemma that is supported by those other features. Okay, automated search. As I mentioned, I had intended to discuss the automated proof of Gödel's incompleteness theorem, but this has to remain unsaid. Some concluding remarks. What about returning to the starting point of my considerations? Hilbert's 1917 call for a theory of the specific mathematical proof. I think we have taken steps towards such a theory by introducing logical calculi that reflect crucial structures of ordinary mathematical arguments and allows the formulation of strategies for the construction of formal proofs. And with that, I would like to thank you for your attention and conclude. Thank you very much.
Thank you. Thank you very much. So now we still have a few minutes for questions, remarks. So first I would ask for this last talk, then we can open to others if there are still some questions you want to make. Again, here from the room, just go ahead if you want to ask something, and from the audience, please write to us.
So let me just say then that I found it so interesting that issues that Paulo and Michael in particular addressed are considered from a completely different angle. Analysis of ordinary mathematical proofs and abstracting from them suitable structures, forward-backward argumentation, for example. So there is, in a certain sense, a middle ground where matters coincide. And I think it is interesting and important to recognize that the resolution methods are powerful and yield theorems of interest, but they are not humanly intelligent, most of them. And that's where I started from, to construct, to use techniques of ordinary mathematics to interactively and then automatically generate proofs.
I think we have a question from José Espírito Santo. Maybe you can.
Is it in the chat box? Or?
It's in the Q&A.
Okay.
I can also read it for you if you prefer.
Yeah, I think that's very nice because oh, wait a second, I have to go to the... Oh.
So,
I mean, in a certain sense, that is of course true. Namely that integration calculi are equivalent to focused sequent calculi. That's how I present it. But I mean, the point is that these focused sequent calculi proofs are directly translatable into normal natural reduction proofs. So in a certain sense, what was one of, if you wish, interesting mathematical logical problems, namely to prove the completeness result directly for normal natural reductions, and thus make automated proof search for natural reductions possible. That is resolved. The completeness proof for the integration calculi for both classical and intuitionist first-order logic give you exactly this strengthened completeness theorem. If phi is a logical consequence of gamma, then there is a normal proof that does the right thing. And to mention in the early 1990s, and even now, it is still considered that automated proof search is not really that natural reduction calculi are not really suited for automated theorem proving. And this clearly is not correct.
Okay, thank you. Maybe you can just give a fast answer to Oliver Kuhlmann questions. He just did 2 comments just before José Espírito, and then we close the session.
To me, it's better to leave the human side to a final try. So I'm not quite sure. What is the question, Isabel, you wanted me to address? There are 3 questions from Oliver.
Just pick one. I mean, he says at some point that it seems to him that one should make a difference between the human interface and the underlying machine.
Well, that is obviously necessary if one does use a theorem prover that does not in the first place use the human techniques. And that's exactly what we're trying to do. That is to obtain, if you wish to put it into psychological cognitive terms, to have a computational model of logical reasoning. Then the interface and the underlying machinery should be correlated in the most intimate and direct way. And to end up with this remark, to connect it to a remark I made earlier, namely to construct an appropriate proof tutor for logic instruction. I have built with lots of colleagues, students, a fully web-based logic class, and it's called Logic and Proofs. And in it, the strategic construction of natural reduction proofs is the primary pedagogical goal. And we have built now a proof tutor that does exactly what I described earlier. Namely, if a student tries to obtain a natural reduction proof in the interface and finds difficulties, he or she can appeal to the proof tutor. The proof tutor gives a partial proof to the automated theorem prover. And the automated theorem prover, possibly with backtracking, completes the proof. And based on this completed proof, the tutor can give hints. But again, that requires that the found proof is found by the proof that has been found by the machine, uses strategies that the human student is supposed to learn. Otherwise, it's obviously hopeless.
Okay, thank you very much. I think we have to close, and I would like to close this session, Automated Proofs in Mathematics, just by thanking to the speakers, to Paulo Oliva, to Michael Kenyon, to Pedro Quaresma, and to you, Wilfried Sieg. We had very interesting talks, and I also want to thank, of course, our audience, and saying goodbye to you. Thank you.
Thank you.
Thank you.
Thanks, Wilfried, for the nice talk.
Thank you, Paolo. It was really interesting and good to see you. I never met you, as far as I know, so it was wonderful to actually see you and hear you. Thank you.
Okay. See you.
See you. Bye.